organizing committee for inviting me and to be here in Canada. It's really the first time that I'm here, so I enjoyed that very much. And the title of my talk is Research Strategies to Approach the 50% Barrier with multi-junction solar cells. And I will introduce a little bit more what we are doing at Fraunhofer in the field of 3.5 and also in a more broader sense. So to start with, as a kind of introduction, I can say the general aim for our R&D in photovoltaics is to increase the efficiencies, but to keep the cost low. And this should be valid on cell level, on module level, and on system level. Because at the end, I mean, we are interested in to have a low cost for the energy production. That means the levelized cost of electricity should be low. And I defined here the cost of levelized cost of electricity in a very simple manner. I don't want to go into the details here, but you see, you can say it's the total cost which we have for the installation and maintenance of a PV installation divided by the lifetime energy production. And if you say in a very simple manner the lifetime energy production is efficiency time irradiance during the lifetimes, it's very easy. Then you see immediately that the efficiency is very, very important. And to sketch that is here, sorry, a diagram shown. Oops, where's the pointer here? Where you can really see, we assume fixed costs, more module prices, and then you see independent what other assumptions you always use. But if you sketch it against the module efficiency, and you see the module efficiencies are fairly high. So these are realistic number for CPV systems. But what you basically see, if we increase the module efficiency, and that means also the cell efficiency, we decrease the cost on the real production of energy, the levelized cost of electricity. So this highlights again, efficiency is very important for our technology. So now let's look what is really possible with the photovoltaics, and I really say photovoltaics. I don't talk about here about solar cells. It's really the conversion of a monochromatic laser light radiation, which is displayed here. So you see here in the diagram what is again called the monochromatic efficiency, and you see it end up to 50%, and it's versus the incident power of a laser light. And you see here it's a maximum. That's very typical for our photovoltaic devices. So at the beginning you have an increase due to rising voltage, and at the end you have a decrease here with higher power, incident power, because you have ohmic losses. So what we can see here, this is a gallium arsenide tiny solar cell shown here, illuminated with laser light very close to the bandgap, with a monochromatic light source and a single semiconductor material. We really have high efficiencies. These practical efficiencies are close to 60% now. So what does tells us? This shows us the photovoltaic principle works in principle very nicely with very high conversion efficiency. There is no fundamental issues. But now I put a but. We are looking for solar cells, and as we know, we do not have a monochromatic light here. We have a spectrum, and this is displayed here, and this is just in 3 different spectra which we know, which are typically used in photovoltaics. First in blue, it's what we call AM0 for air mass 0. It's outside our atmosphere in the space. So these 3.5 solar cells, multi-junction solar cells, are typically developed or originally developed for the use in space for satellites, because we have the high efficiency. And then if you go on Earth, you see here we have the Earth's atmosphere, we have absorption within our atmosphere due to water and CO2. And then we have to distinguish 2 spectrum. One is AM1.5 global, which means this is the normal resources which is used for flat plate. And if we go to concentrated light, we can only use the direct spectrum. So we have less blue content here. You see it a little bit. So there is small differentiation between the 2 spectrum. And you see it's also an AM air mass 1.5, but you see here this is the direct spectrum. So what does this mean for the PV efficiency? Now we can do a very simple calculation. This is shown, and I think it's most of you well known, what is called the so-called Shockley-Queisser limit, where we assume here one semiconductor material. And what this diagram shows you here first is the efficiency calculated versus the band gap of a semiconductor material. So what does it mean? On the right hand side you have a high band gap, so you can obtain a very high voltage at the end with a solar cell having this high band gap, but you have a very low current. On the other side, on the left hand side here sketched with a low band gap, you generate a high current but a low voltage. As you know, the product of voltage and current is our power, and you see we have a relatively broad maximum for the different spectrum. And you see it's also important to recognize it depends really on the spectrum. So if we have the M as 0, we have at the end a lower efficiency if we compare that to the so-called R mass 1.5 spectrum. And now also very important to see the green line. This is now efficiency calculated under concentrated light, also for the AM 1.5 spectrum, but you see here in detail this is at the concentration level of 1000. So it's important to note that the efficiency under concentrated light rises for intrinsically, even if we have the same band gap material. So that's very important. That means concentrating of sunlight rises the efficiency. So what are the limits if we have only one material? And this is sketched in this diagram here, where you see here in the gray color the spectrum of the sunlight here again, and in the red color here what is convertible by a, in this case, silicon solar cell. So photons actually which have too high energies, sketched here in the blue, generate too much or have too much energy, so they generate or go in within the band structure much above the conduction bands, and loses the energy by thermalization, so it generates only heat. If we have too low energy in the photons, it cannot be absorbed at all, and we call these the transmission losses. And basically, to simplify it a little bit, all what is shown here in the gray area are losses for the solar cells. So what can we do to increase the efficiency of a solar cell? And the simple answer is we have to manage our photons. And there are in principle two ways. One is more on the optical part, so we can shape our sun spectrum and use one semiconductor material. And some of these approaches are well known, and I don't want to discuss it here. We call some of these solar thermophotovoltaics, where we have an absorber which transmits the broad solar spectrum into a monochromatic light source. We can have up and down conversion or optical fluorescence concentrators. And the second part, which I want to talk about, we shape the materials. So we don't talk anymore about one single material, but we talk about several semiconductor materials which have different band gaps. And this is commonly well known as the multi-junction solar cell approach, which you can realize in a way that you can talk about mechanical stacked or monolithically grown. So what is the benefit of that? Because we have different band gaps here, you see we have basically the same shape, but starting at these different band gaps. And now what you simply see, our transmission and transmission losses as well as thermalization losses are dramatically reduced by simply comparing the gray area. Again, this are the losses of a solar cell. So that means we can achieve much higher efficiencies with multi-junction solar cells. As I said before, we can realize that in a mechanical stacked approach, which is seen on the left-hand side. You start with a typical solar cell with a high band gap and stack that on top of two others with decreasing band gaps. Or what is more smart, you put these solar cell into one structure, and then you have only, as for a conventional solar cell, a top connection and a bottom connection, whereas here you have basically 6 wires, which is realize the outcome of this solar cell. So at Fraunhofer East, actually, we did a lot of work in this mechanical stacking approach with different optical concepts, as can be seen here. For example, in the early days, we did a triple-junction solar cell, which was also at that time a record solar cell. That was already in 2001. We made also nice optical designs to realize spectrum splitting beams. And I would say this technology is very, very interesting and also physically of very much of interest. You can learn a lot. But if you look into systems, it's really not cost efficient. I mean, we went through all the cost calculations and found if you go to these more complex system integration, you lose really the benefit of the high efficiency. So it's much more smarter to go to a monolithic grown structure. So and this slide shows you what we can expect basically from a multi-junction solar cell. This is again a calculated efficiency limit based on Shockley-Queisser approach, but now looking what is the optimum band gap if we look for different junctions. So what is shown here is always the band gap energy of the different materials to get this efficiency under concentrated light. In this case, the calculation assumes a 500x concentration. In reality, we know that from these limit efficiency calculation, if you look to practical devices, we can, as a rule of thumb, achieve 75 to 80%. And if you look to that, and we are aiming for 50% solar cell, you can also see easily that we have to go for a more or less 4-junction solar cell, because the theoretical limit of a 4-junction solar cell is 68%. If we go to a triple-junction solar cell, so you see it's roughly 60% in theory. So with a triple-junction solar cell, we end up in maximum in reality with an efficiency of 45 to 47%. Then we have to add another junction. And what we are doing here is we develop in our laboratory different solar cell architectures, as we call that. All these solar cell architectures which are displayed here have the potential to really achieve 50% conversion efficiency in reality. I don't have the time to go into this during the talk because it's too many details on that, but I just want to mention there is one approach, what we call lattice-matched 4-junction solar cell grown on a germanium substrate. Then we have a so-called inverted metamorphic approach where you grow the solar cell structure in an inverted structure, meaning that you have a substrate like gallium arsenide and you start with the high bandgap material and then you grow the lower bandgaps and you turn it around afterwards and remove the substrate. Then we have also ideas for 4-junction solar cells where we have a bonding layer in between. And also this is true for a 4-junction solar cell on gallium antimonide substrate. And then we have at the end also a 4-junction solar cell where we use engineered substrates. So what you see here, there are different combinations of 3-5 materials. There are names like metamorphic, bonding, and different substrates. And that brought us to the idea to show here what we call now manufacturing toolbox to making 3-5 high efficiency multi-junction solar cells. Basically, if you follow these lines, I mean, you need a substrate to grow your material, you need a technique to grow your material, then you have different growth concepts, and at the end you have, after you have grown your epitaxial layer, you have to process your solar cells. And you see here, the variety really increased over the last years, actually, what materials we can use, also in terms of epitaxial methods. The majority is still metalloorganic vapor phase epitaxy, and then we have different growth concepts, which we have all under investigation, and we really combine it to get the highest efficiency. What I will show in the follow-on, I take out some examples to explain a little bit more in detail. Unfortunately, I do not have the time to go through all the different technologies. And what I want to start with is also to start what is the current status of the industry. And this is highlighted here. It's an industrial, and you see here what we call upright lattice-matched triple-junction solar cell, where we start on germanium. We use as growth technology metalloorganic vapor phase epitaxy. The structure which is grown means upright. It starts with the lowest bandgap, and the bandgap is increasing. And important, all the materials which are grown are lattice-matched to germanium. And definitely after you have grown the structure, you need your grid design, you need metallization, and you need also a standard anti-reflection coating. So to show that, what does this mean? It's more in detail presentation given here. This is the typical triple-junction solar cell where you see here you start with a germanium wafer. During the growth process by MOCVD, you see here a typical reactor. There is an indiffusion into germanium to generate a PN junction. Then you need to interconnect this bottom solar cell via a tunnel diode. This is basically an electrical contact to the next solar cell, which is the gallium indium arsenide middle junction solar cell. Actually, there's only 1% indium in, because this is exactly the combination which gives the lattice-matched condition to germanium. And you see the structure of such a solar cell typically has an N and P doped layer typically, and also surface recombination layers to reduce the surface recombination on the front and on the back side. And then it follows another tunnel diode to connect the top solar cell, which is basically the same. So what you can see, a typical triple junction solar cell consists of 15 to 20 different layers of 3,5 materials. And if you look into the details, you found here binary, ternary, and quaternary materials. And it's the knowledge to really grow these materials with high reproducibility. But that's possible in industrial reactors, like it's shown here, an MOCVD reactor. And in typical production efficiency today from the industry is in the range up to 40%. The record efficiency for this structure is 41.6%, achieved by Spectrolab already back in 2009. So what is the problem with that structure? I mean, we want to increase the efficiency, and one important concept which we were looking into is the so-called metamorphic concept, and I want to explain that. What does this mean in the next step? So to introduce what is metamorphic growth, I start here with the land or map, which we typically say of our 3,5 materials, where you see here the band gap energy and versus the lattice constant. And I said the industrial standard is a lattice-matched approach. So you see here germanium, gallium indium arsenide, gallium indium phosphide has the same lattice constant. And you can imagine if you grow and you sort your atoms on top of each other, that means you can get the best material quality because there is no really chance to have any failure in the material itself. But we can go to much more. You see here the lines here showing from gallium arsenide to indium arsenide. This is gallium indium arsenide, so if we increase the indium composition, we change the lattice constant. The same is true, for example, for gallium indium phosphide. Or if we go to gallium arsenide nitride, whatever. So these lines are always the ternary materials combination between different binary points. So now, what is quite interesting, if you do a theoretical calculation and look for the highest triple junction efficiency, you find that actually not this material is the best combination, but to lower the band gap of the top and the middle cell. And if you do that, you see it's no more lattice matched to germanium. And that is what we have to make somehow a growth technique which allow us to grow a new lattice constant on top of our germanium substrate. And this is called what we call the metamorphic growth, because we start to grow a buffer which generates a new lattice constant. And the whole aim is, and this will be explained a little bit later, that we have all dislocations located in this metamorphic buffer structure so that we can grow a very good material on top of that. And quite interesting is the material which Karin mentioned, to start with silicon, because if you look to the main cost of 3,5 solar cell, it's actually the substrate. So the cost for the germanium substrate is roughly 50 times more than for a silicon substrate. So it would be very nice if we can grow our 3,5 materials on silicon. But if you look to silicon and go for this gallium indium phosphide gallium arsenide, which would fit very well for a triple junction solar cell, you see we have to overcome a lattice constant of difference of more than 4%. But one approach could be to use this metamorphic growth concept which we have developed over the last years. And actually this idea is very old. to give this example of metamorphic structures, it was already published before 2000. Then in 2009, Fraunhofer achieved the world record for these metamorphic growth structure conditions. And actually this technology was directly transferred into industry. And today you can find by the companies Spectrolab and Azure that the highest efficiency product have always metamorphic structures. So I think that shows very nicely that to develop a new product you need also some time to develop this technology, but at the end I think we could really put that very quickly into an industrial product. So to explain a little bit what does it mean actually, what is the problem of the metamorphic growth, I brought this diagram here with me. You see here more or less the substrate could be germanium, for example, and the lattice constant is very regular. And then on top of that we want to grow a material which have a larger lattice constant. And what happens, this is our buffer, we have to adapt the lattice constant in a certain way, and you see here to get this adaptation we have some defects to really get it fitting together, and what we call misfit dislocation. As long as we can locate these misfit dislocation within this layer, they are not harmful. But sometimes it happens that some of these dislocations are running through the active materials, and we call these threading dislocations. On the right hand side you see here now a transmission electron microscopy image of such a ground structure, where you see here the germanium substrate here. Then we start our growth, and then you see the dark lines are really these misfit dislocations. So they are in parallel in the line, so they are not harmful at all. But then you see, if we stop our buffer layer here, you see some of these dislocations are running into the active material, and they are very harmful for the solar cell. So we spend a lot of efforts to understand this metamorphic growth to avoid these threading dislocations. So we made a lot of investigation on different buffer schemes, as can be shown here. So starting with constant buffer, linear graded buffers, step graded buffers, and you see here always transmission electron microscopy pictures. So that was a lot of work. At the end we understood that the best way is to go with a step graded buffer, and that was always analyzed by investigation of the threading dislocations, and it's not easy to really investigate that. We developed the Cathodoluminescence technique as it is shown here. So you see here Cathodoluminescence image of a structure where we just stop our growth after the buffer growth, and then we really counted the dislocation densities. And what you see here, different pictures of that. So here we have a dislocation density in the range of 10 to 5, but here we have dislocation densities in the range of 10 to 6. So what we typically should have is definitely for a metamorphic structure, so you see here the ternary material with 29% indium, which should be less than 10 to the 6 of these threading dislocations. And why do we need that? This is simply shown by a calculation already back in 1985 by Yamaguchi et al. They showed how the open circuit voltage will be influenced by the so-called threading dislocation by using a very simple two-diode model. You see here is the density of the threading dislocation, but I think basically you can see here what happens. For a gallium arsenide solar cell, so the open circuit voltage means stays more or less stable for a certain dislocation density up to 10 to 5, but then it drops rapidly because the diffusion length in the material is now more sufficient and the dark current increases. So the general aim is that we have buffer developed which have a threading dislocation density less than 10 to the 6. And to demonstrate that in a practical device, I show here two internal quantum efficiencies of, again, a ternary gallium-indium arsenide single-junction solar cell, where you can see here, first, if we have high threading dislocation density in the range of 10 to 7, we see that it's also very much influenced by the current. The internal quantum efficiency is much less because the diffusion length is not sufficient. But even more dramatically, you can see it on the open circuit voltage, which is much less than for these devices, which have a threading dislocation density in the range of 10 to 6. So if we're looking now for 3.5 on silicon, I mentioned that we have to overcome a 4% lattice mismatch. And very recently there came the idea to start, okay, we go a different way to grow that. In the earlier days you were directly growing gallium arsenide on silicon. Now if you look in our map, you see gallium phosphide fits very nicely to silicon. So if we grow and start gallium phosphide, and then we made a metamorphic growth down with gallium phosphide arsenide, that is a very promising approach. However, if we grow on silicon, we have another challenge to face, because gallium phosphide is a polar material, so you have gallium and phosphor. And if you start growing on silicon, you have sometimes steps. And you see here, for example, this is a single step. And if you then start with a nucleation of a phosphorus layer, you see we have a distortion in our lattice in the gallium phosphide. And this is so-called anti-phase domains, where phosphor-phosphor bonds happens, which should not happen at the end. And when we started that, it was very obvious that this is a big problem. So this is also a TEM picture here from the University of Marburg made on our samples, where we start to grow gallium phosphide nucleation layer on silicon. And all these dark triangles are basically these anti-phase domains. So we optimize the growth conditions, and then you can see after optimization of these growth conditions, you can get nearly perfect gallium phosphide material on silicon. So now we are back on that point, and we want to use the metamorphic structure to overcome the 4% lattice match, going this way as it is displayed here. And you see we grew again the stepwise buffer with a lot of dislocation, but so far we were not successful to really avoid all threading dislocations in the gallium arsenide active layer. And you clearly can see that in the results which we have for the moment for this approach, where you see in the blue color, this is a dual junction solar cell grown on gallium arsenide solar cell material as a reference with high external quantum efficiency. If we grow it on silicon, you see again what we saw before for the gallium indium arsenide. We lose a lot of current, and if you look also onto the voltage, we lose a lot in voltage due to the very high dislocation density which we have in this material. So another approach to overcome that is, let's go to a new technology which came up very recently, and this is bonding technology. So the basic idea is you grow a structure here on a substrate like gallium arsenide without any dislocation density. You have a n-junction in silicon, and you put both semiconductors together, press it together, and then you have more or less a conductive interlayer in between. To do that, you need a special equipment. This is called a surface-activated bonding machine, which we have available at Fraunhofer ISE. You see here in principle the photograph of this machine. This is the inner part. So you have two wafers here on top and on the middle, and you have vacuum. You do a deoxidation of your surfaces, and then you press it simply together, and you do a short anneal at low temperature and put some forces on top of that. So this is a magnification of the cleaning process with a plasma within the wafer. And then if you look at the end, again, in a transmission electron microscopy, you see here the silicon cell and the gallium arsenide cell, gallium indium phosphide cell. And in between it's just a layer which is really an amorphous structure. This is simply because you put together these two crystal materials and you put some forces on that, and in reality you generate an amorphous interlayer. So the question is how this interlayer behaves electrically, and we made experiments on that. And what I just want to mention here very briefly is it works very nicely, because if you optimize your bond conditions, the interface resistance is fairly low, sufficiently low to really make solar cells out of that. So we did that. We started first with gallium phosphide, gallium arsenide on an inactive silicon silicon substrates, and this is a tandem solar cell on one sun, AM1 global efficiency, AM1.5 global efficiency, which is 26%. We made recently also the first attempts to use activated or active silicon solar cell, and you can see here basically the results out of that. This is the external quantum efficiency of this triple-junction solar cell made on silicon, active silicon. And you see here, this is, by the way, a concentrator solar cell, which you can also see it's a very tiny solar cell and achieved an efficiency of 30%. It's still limited in the concentration ratio, and there are still open issues, but we believe that is a good way to go also for the flat plate applications, because at the end we need also to increase the efficiency, and we have to ask ourselves what is beyond silicon at the end. And there could be one solution, the 3-5 materials. There could be perovskite on top of silicon, and maybe we hear something in the next talk about that. So now, the topic 50%. What is possible for 50%? And I go briefly to some approaches which we have at Fraunhofer East, and you see we are looking here for gallium arsenide germanium substrates. We use here mixed structures of inverted and upright growth with metamorphic, and in the technology it's always based on wafer bonding technologies, which includes also a kind of lift-off because we have to remove the substrate, and we need a broadband anti-reflection coating to have really high efficiency. The first approach which we are looking now very recently into is we still go on with the germanium substrate because this is well known in industry, and we can grow here with a metamorphic structure a gallium arsenide solar cell. We have proven that, and then we bond here on top of that a gallium phosphide gallium arsenide structure, as I have just shown with the silicon substrate. So what does this mean? So you see here the growth of this metamorphic structure, and you see here inverted growth. Inverted means, again, you have a substrate and you start with a high band gap and a low band gap. Then you put that on top of each other. You make actually the bonding, and then you have to remove the substrate, and then you have a 4-junction solar cell device. What is very important for this bonding is the interface. And specifically, if you go for metamorphic structure, I have shown that the surface is more critical. We have sometimes bowing, and so we spend a lot of time to understand that and to optimize also the growth structure. So this is the surface with an atomic microscopy image directly after epitaxy. What you can see, the surface roughness scale here is going up to 4.6. And we know from our experiments that with this surface roughness we cannot make a good bond. So what we do is we do a surface polishing after the growth, and then we can come down to a surface structure roughness of less than 1 nanometers. And from our experience we know that this surface roughness is sufficient to make successful bonding. It's also a technology which you have to develop, and I show this here by the scanning microscope, acoustic microscopy images, where you see in the light spot, these are non-bonded areas, and you see here a lot of difficulties before we start the optimization. After the optimization, we still have some issues here on minor points, but it looks very nice. We had made some first solar cells out of that, and we adapted also the structure, as you can see, to fit really the count between the subcells. We have to add a little bit aluminum. We made the design in a proper way. So now we have a very nicely performing 4-junction solar cell on germanium with a very good current matching condition. We have also made some first solar cell out of that. And you see here for the 1.5 one-sun application, so on large area, the efficiency is in the range of 35%. It's something which is promising. It's not the very best for the moment. And then we measured it under concentration and got an efficiency of 38%. So this is definitely not what we want. So we still have here some limitations in the series resistance, and we have to work on that concept more actively to get it really to 50%. But I want to show that that's a typical way how we have to optimize with our toolboxes, which I have shown before, to get really to 50%. It's not that you put all the material together and you immediately have 50%. It's really hard work to develop these complex structures. So another approach which we are looking into and which is more successfully developed recently is based, and this is now the highlight here, engineered substrate. And this is a structure which is based on engineered indium phosphate substrate, which we developed together with the company Soitec. So why is that of interest? So if you look here again to the best material which you grow on indium phosphide and on gallium arsenide substrate, and you calculate the band gaps theoretically and what you can achieve practically, this is shown here, the ideal values from the Shockley-Queisser and what are really achievable. You see that's very close if we have really a possibility to grow an indium phosphide substrate, because then we have no metamorphic growth, so we can really realize the highest performance in the materials. However, indium phosphide is even much more expensive than germanium, so you need another idea, and this is the competence of the company Soitec. While they started this activity, they have a so-called SmartCut technology, which is shown here basically. So they have here on a 3.5, in this case indium phosphide, they really can transfer very, very thin layers down to 50 nanometers and put it on a different substrate. This is shown here. Again, this is a 4-inch wafer after the SmartCut process. And basically what we get at the end is that we have a gallium arsenide substrate. On top of that is a small indium phosphide layer. And then we can grow on these layers our structure. And this is shown here. So we have made a 4-junction solar cell where it's on engineered substrate actually, where you go with lattice-matched material of gallium indium arsenide phosphide, then you bond the inverted structure again. On the right-hand side you can see where we started some years ago. Actually this bond shows also that there are some failures, and I have to mention that this bond was made on a bulk indium phosphide material at the very beginning. Then we optimized the bonding process, again still on bulk, and very recently we could really use this engineered substrate where you have only this very thin indium phosphide nucleation layer, and after all the developments we could also show that this bonding is very perfect and that we can get very high efficiencies. And this is shown here. These are the world record efficiency for any photovoltaic devices. So it was measured here at Fraunhofer with an efficiency of 46.5%, and I pay your attention on the uncertainty, which is for these very difficult devices because it's very difficult to measure. And it was also measured in ice independently, showing an efficiency of 46%, so this is very well within the uncertainty. I don't have the time to go into the details what are the reasons for that. This is really another talk. But we are very happy that we are very close with these two measurements and confirming that we have an efficiency of 46% realized. So now we use these solar cells also and put that into applications. So the very first cells, and it's not a single cell which was made, it was really on wafer, it's an industrial process. So we could use that and put that in our technology which we developed. We call that FlatCon, which abbreviates Fresnel lens all-glass tandem cell concentrator. Basically you have here a Fresnel lens which focus the light on these tiny solar cells here. We made a module here out of 52 cells, and then we put it on sun at Fraunhofer, and then you see here the measured data. And out of these measured data, we have developed within the standard of the IEC technology to develop really what we call the concentrator standard testing condition, which are given at 1000 watts per square meters and a temperature of the cell of 25 degrees. So if you do all the translation of these measured data, you end up in an efficiency of 36.7 on module level, which you compare to the standard measurements of a flat plate module, which is in the best case of 20%. However, very recently, and this is a data which is not yet fully published, I'm happy to get the release from Soitec. They made also a module, and we measured that module at ISE, and I can tell you that we have now much higher efficiency, which is 38.9%. So this is very promising because we are approaching the 40% module efficiency now. So to put that all together, I brought this slide here with me. This was actually when I worked on the strategic research agenda for the European Commission. We developed this plot. There we had data, and I called that practical efficiencies, because at that time we didn't have any standard to measure it, so all the module efficiency were measured outdoors. And what you can see here, these are the historic data point up to 2011, and then I made a projection what we can expect in the future. And over the last 4 years, the recent values followed very nicely these lines on the cell level, and you see here now the record efficiencies which we have is 46.0%, which was achieved with this bonded structure by ISE, Soitec, and CEA. But there are other structures around, for example, the n-GaAs structure, which is an inverted metamorphic 4-junction solar cell, which is very close by. I would say it's practically the same efficiency. And I'm sure we are not at the end. We can really expect very soon also the 50%. It's really the question now whether we obtain this 50% only in 2020 or whether we can accelerate here. So this is an open question. We work hard on that to get the 50% much earlier. But what is of interest to put that into real applications, so into the modules. And here is a line. So since last year we have really a new standard to measure the solar cells. And that is why we have two different ways to do that. This is the concentrator standard testing condition, which I just mentioned. And then we have the concentrator standard operating conditions, which are more realistic, I would say, and more related to the practical efficiencies, because these are outdoor measured efficiencies. So what you can see really, these newly record efficiencies are above the line, because these are according to the new standard. And if we follow the more practical efficiency, it's well online. And at the end, you have to put the module into a system and looking on AC system efficiency. And the best values which we can get here in literature for the moment are system efficiencies close to 30%. To put that together, what is the status of the high concentration CPV? I put here the cell efficiency again. These are the typical industrial efficiencies for the moment, and these are more or less the record efficiency in parentheses where we are for the moment. And with that, I like to conclude here my talk in a way that I can say the multi-junction solar cells, or the technology, is continuously progressing over all the years, and it will continue, I'm sure. The actual status is that we have achieved an efficiency of 46% for wafer-bonded structure, and out of these cells we could realize module efficiencies as high as 38.9%. And definitely, I hope I have shown you that we are on the way to 50% and 40% module efficiency, 50% for cells. And to do that, we need really a huge variety of what we call technology building blocks. So we are working on all these different aspects, and then we try to put this together. It's sometimes not an easy task, but anyway, it's a very interesting task. A lot of physics and technology development is behind that. If you are interested in more details on CPV, we recently published a report on the status of this technology together with Annual, and you can download that from our web page. Finally, last but not least, I'd like to thank specifically my team at Fraunhofer ISE and all our collaborators. We are really very well connected internationally with several groups to really get these high efficiencies. And finally, I'd like to thank you for your attention, and I'm happy to answer your question. Thank you. That's a really good question. The colleagues from the industry, they tell you, yes, it's worth to do. To be honest, we have to develop the technology in a very smart way, because bonding technology introduces definitely another step of of complex technology. But the people telling you from the system part that it's worth to do if you achieve a certain cost level, that's for sure. I mean, I said in the assumption that we have to keep the cost low if we introduce a new technology. That's absolutely the key. But on the research part, I have to say we started somehow at very, very high cost level. And I can tell you when we founded, for example, Concentrics and we made cost analysis on CPV, we couldn't imagine how we can come down with the cost to the costs of today. And in reality, we did it. Because if you start continuously working, you have new ideas, you bring down, you make your technology more easy. But definitely for these small-junction solar cells, if it's introducing bonding technologies, they are more costly. But I can tell you another nice story. I didn't talk about that. We are working also on this lattice-matched material gallium nitride arsenide. And if you do that, you find out if you make a 6-junction solar cell, which is more complex, has 50 layers in it, the total thickness of this structure is less than a 4-junction solar cell. At the end, it's cheaper to do it. So you have to look into the details, but there are other difficulties. I mean, we have to get the high efficiencies, that's the primary goal, with low cost.
Andreas, wonderful talk. So you've been really working hard at targeting 50 and you're close, it's in sight. What happens in the next 10% if you want to try achieving 55 or 60%? Does the efficiency increase, let's say on a per year basis or a per investment dollar basis? Does that start slowing down?
I mean, as a scientist, I'm very much interested to get the highest efficiency as possible. But in reality, you have to look what is the real benefit. I mean, it goes a little bit in the same answer. We have to look on cost. And in addition, as said, the efficiencies are really measured in laboratory. If we go outside, we all know that we have Orion spectrum and we have to look on the influences of the spectrum. So we published also a lot on that already years ago. What is the influence of the spectrum if you go to more junctions? Is it beneficial or worse? And I mean, at the end, it's very surprising. Didn't expect that. It's still a benefit if you go to higher junctions. If you look on a daily specific point, it's maybe disadvantage. So now it depends really how you integrate it in total in your system. But I personally would say if we reach the 50% barrier, I mean, there is definitely a lot of interesting research to do. But in real application, it makes not too much sense to go really, or to spend a lot of money to get 52% at the end. There is a big difference because because you have the optics, you have always a distance between the cell and your optics. That makes actually the module in the height much higher than a flat plate module. I mean, typical concentrator modules, you find varieties in the market, by the way, from around 70 millimeters up to 200 millimeters. And that makes you integrate your solar cell, and then you have an environment where you have some air, you do some protection, but you do not have a full lamination process. Even so, sometimes you need a secondary optics, and then you integrate your cell with a secondary optics. Then it's a little bit like a lamination process in a flat plate module. But it's another complexity which you have to solve for high reliability. But it has been proven in the community that the CPV modules are running very well also for 20 years.
Well, can I ask you about the 3 thoughts on silicon? The future, you think it's going to be for large farms? Does you still know what's your take on 3 thoughts on silicon?
I mean, we are still far away to be cost competitive. But also I talked a lot with our silicon colleagues and looking also in the strategy for the photovoltaics. It's very much clear that at a certain point we come at the end for the efficiencies, and as I shown or tried to introduce, the efficiency is very essential. So for the moment, I would say, cost-wise, we are far away to have this in the market. But learning from my experience in the back, we have to approach it. I mean, if we do not have an experience how to make it, or how to approach really the 3.5 on silicon, I mean, we can never answer this question fully. I'm personally convinced that we can go, for example, with a bonding technology, 3.5 on silicon, and in the combination maybe also with engineered substrate, we can go really to very nice high flat plate module efficiencies in the range of 30–35%, and this pays off at the end. I mean, again, depending that we make the production technology not too expensive. But this is more long-term vision, in the range of 10 maybe years, maybe even 15 years. It's very difficult to say. But for us, it's very important because we are now in a way to go the next step for photovoltaics. Yeah, we actually don't need it. I mean, on the back side, you need definitely also, because if you had a close look on that, I didn't went into the details, but if you look, what was really the limit for this cell was the silicon solar cell. So you see here, here we have only 10 milliamps in the bottom cell. So if we can increase that, but that means backside optical confinement, where we don't need intrinsically texturing. We can also look for other approaches, taking over from amorphous silicon, for example. Photonic structures is one target we are looking into that. But we don't need a front side texturing at that point. And on the back side, we can do it in principle. That's not a problem. But for the long wavelengths, it's not really feasible. I think there is much better approaches to solve that.